we'll get started for the day, and wait for the usual trickle of people into the classroom. A couple announcements before we start. First of all, your project instructions are on the course webpage, as is homework 3. Right? So basically, your remaining responsibilities for the quarter are homework 3, homework 4, and this project is posted. And hopefully none of these will be so bad. I guess if you haven't been described yet, then that's also your responsibility. And in case you didn't see last night, I also posted a request for an additional scribe for 4 lectures for which we don't have folks doing it yet. Yeah.
We might for one.
Okay, great.
Don't forget to send us your negotiation position.
Exactly. So we offered late days in exchange for that. If you don't want that, if you want something else, then we're willing to negotiate. But you'll have to name your terms, and we'll figure it out. Another thing, I've heard some folks struggling with problem sets and turning in late. I thought I'd give you a quick reminder, since we're at about week 5 here, that office hours exist, and they should be used. And they happen after lecture on both Monday and Wednesday. And also, Diana's office hours are Monday afternoon. Yeah. So please come. We're happy to help you out. We'll probably give too much away, at least I will. And we prefer that you learn the stuff rather than having to do the usual last-minute scramble to get it all together. So any questions about procedural stuff? No? Cool. All right. So today's lecture is on a topic that is very close to my heart and is certainly sort of the bread and butter of much of the research that we do here at Stanford, as well as much of the research that goes on in general in geometry processing and some of these applications of differential geometry on triangle meshes. So I thought it would be worthwhile to spend a whole lecture today deriving basically one operator called the Laplacian, which is humongously important for any number of reasons, and we'll try to justify why in just a few moments. Before we get started, a couple of things that you should know. First of all, for some reason in the computer science literature and in the math literature, the Laplacian has opposite signs. I think in the math literature, it tends to only have positive eigenvalues, and for us, it tends to have negative eigenvalues. Chances are, in my lectures, since I'm interpolating between about 6 or 7 different papers that I was reading and trying to help you guys get some intuition for it, I might make stupid mistakes. And you should know that if there's a plus or minus, you can A, raise your hand and tell me that I made a stupid mistake, and B, just keep that in mind. Especially on your homework that's due in about 2 weeks. One of the main things that I'll be asking you to do is simply to implement the Laplacian operator that we're going to discuss today, probably ad nauseum. And one good hint for your homework is that if your Laplacian doesn't seem to be doing what you think it should be doing with plus sign in front of it, before you do any other debugging, just stick a minus sign in front of your Laplacian and see if everything works. This is, of course, an engineering solution rather than a rigorous mathematical argument. But since all of the literature in this field flips signs back and forth every 2 years, depending on the weather and whoever is writing papers, it is important to know that when you see this triangle, it could mean plus or minus what you think it means. Anyway, consider yourself warned. Also today there'll be lots of math. So please, usually I draw lots of pictures and kind of try and operate at mostly an intuitive level, but today we're going to have lots of symbols and equations and things. And the second that you don't understand something, you should stop me, because you will be implementing about 80% of this on your homework. Cool. So today's focus is on this operator that is called the Laplacian. It looks like this. It's a delta, capital D. And the Laplacian, you can think about it as sort of a linear functional. In general, what is a functional? Actually, we got some questions about this on homework 1. I guess this isn't vocabulary where we define some of the left. A linear functional is sort of like a generalization of a matrix. It's this linear object. In this case, it takes in functions on a surface, right? So C infinity of m means that these are infinitely differentiable functions on a surface, right? So they assign one number to each point on your surface. And basically, all it does, our linear functional, is going to give back another C infinity function on m. In particular, we don't have a huge intuition for what it does on a surface yet. When you have a domain in Rn, this hopefully is an operator that you have encountered in either physics class or math 52 or 51 or what have you. Right? All Laplacian is, and again, remember, right, slide number 1, this minus sign is suspect. I happen to like it. But anyway, all the Laplacian does is sum over each of the coordinate directions and take the second derivative of your function. Notice that maybe this is notation as computer scientists that we haven't really seen a whole lot of, right? That we're like summing together d over dxi's, but there's no like f next to that. And that's because this thing, you can think of this as the derivative operator. Yeah? Is everybody sort of comfortable with this notation or seen it before? Yeah? Okay, good. So I won't spend a whole lot of time expounding on that. So why is Laplacian so interesting and useful and good for our everyday lives as geometry processing experts here? Well, first of all, there's a very strong connection to physics that we all know and love. And the Laplacian just shows up in any number of these sort of second order ODE, PDE looking objects that we study. For example, the heat equation is nothing more than du dt equals minus Laplacian of u. Now let's break this equation down a little bit. This symbol u here stands for a distribution of heat over a surface. Right? So in this little diagram above here, I guess it's colored from blue to red, right? So blue is kind of cold, red is hot, yeah? And there's one value of u for each point on the surface. And all it's saying is that the rate at which u is changing at a fixed point p is proportional to Laplacian, or minus that. Yeah? In fact, I think I already made a sign mistake. But such is life. Right. And why does this make some amount of sense? Well, remember that your Laplacian is nothing more than this sort of second derivative operator. I had too much coffee this morning. And what does the second derivative do? It sort of tells you about the concavity of your function, right? Whether it's facing down or up. So one way to think about the heat equation is if you have a function that looks like this, right? This is some heat distribution. What is it going to want to do to the heat distribution? Well, it's going to want to take the points that are kind of bigger than their neighbors and bring their heat down and bring the heat up of guys that sort of cut the other way around. So it's sort of a reasonable object. Another thing we can do with Laplacian is find its eigenfunctions. If we don't like the word eigenfunctions, you can think of this as eigenvectors and eigenvalues. But basically, Laplacian is just some linear-looking operator, just like a matrix in discrete way. And we can apply our favorite idea of what it means to have an eigenvalue and so on. And in this case, what this yields is actually the vibration modes for a surface, right? So I meant to replace this line with something more intuitive. But if I made the line out of I guess a piece of sheet metal, right? And I took that line and I hit it with a hammer. Right? Then certainly, the musicians in the audience that have used a stringed instrument have experienced this phenomenon. But there are certain frequencies that you're likely to hear, right? And those have to do with basically how you can fit waves into the surface here. And the eigenfunctions of Laplacian are exactly the frequencies that you expect, right? The eigenvalues and the eigenfunctions are the corresponding waveforms. So, how do we define this thing? Now, I've told you how to define the Laplacian for domains in Rn, right? That's pretty simple. We just sum up a bunch of second derivatives. But on a surface, if you recall Adrian's last couple of lectures, right, we have to do a lot more work to make sure that our definitions are involve only quantities that you can measure by moving along the surface, right? These intrinsic objects. So, a lot of times, the way that we write down the Laplacian of a function is we write down this nice sentence here that Laplacian of f equals div grad of f. Right? Have we seen this expression before?
On Monday.
On Monday, great, yes.
It was very small and it was at the bottom.
Right, that's true. This is the very last thing that we did on Monday. And in fact, you see basically exactly this slide a lot in geometry processing lectures. And then they move on, they start using the Laplacian operator. But this begs a humongous question, which is, what the heck are div and grad on the surface? Yeah? And thankfully, Adrian covered this on Monday. And all of these different operators, like divergence, gradient, curl, although we haven't really talked about that a whole lot, admit different types of discretizations, but some of which are sort of easier than others. Right? So if we were to follow the story that we had gosh, in week, 4 or 5, when we were talking about curvature, right? How we go back and try and compute the Laplacian of a function on the triangle mesh. Well, maybe we would go to one of our favorite formulas for Laplacian and see if we can discretize it in a reasonable way, right? But unfortunately, when you kind of unravel all of these nice things that we've built up in this class, we can get pretty yucky formulas for Laplacians of functions. And so today, I think we're going to try and take a parallel view between discrete surfaces and continuous ones. Yeah?
I was going to say, this formula isn't exactly the one that was on the Monday's class. It's the one that I had on Monday's class had the Christoffel symbols in it.
Right.
But it's sort of equally yucky. This is an alternate formula, which is marginally less yucky.
Yeah, I guess this is d sub I, d sub j sort of are hiding the Christoffel symbols.
No, they're not. That's a completely valid formula that doesn't involve any. It involves only organic.
Right, this is
Christoffel symbols are hidden inside the derivative of the square root of the determinant of the vector.
Right. Cool. Yeah, anyway, regardless, either one of these formulas is pretty yucky, right? And if you think about going back to the Christoffel symbols, right, where you're sort of differentiating one direction and another direction and so on, these are very difficult objects to discretize in a nice, consistent way. And so we'd like to go back and find a different approach to the Laplacian operator that's somehow easier to deal with. Yeah. So hopefully this story makes some sense. So probably the gradient of a function is something that actually we're going to define on a triangle mesh in a little bit, and it's not a very difficult thing to do. Unfortunately, divergence is a little harder to think about, and we're going to defer our discussion of how to compute divergence of the vector field on the surface. I guess till next week, right? We decided on tech for next week, yeah. So in some ways, if we start with this definition of Laplacian, we say, well, okay, so let's just we don't know what to do, right? It's if we want to write down a divergence operator, a curl operator, or rather a gradient operator, and just kind of compose them to get the Laplacian. This is something that we will be able to do soon, but it's a little bit trickier construction. But thankfully, there are some ways around this, and today we're going to talk about one that's used humongously all over the place, especially in certain areas of discrete PDE. So let's return back to our example where we just have some domain in Rn, right? Because somehow this is much easier to think about, at least for peons like me that are very bad at integrating things on surfaces. So let's say that we have something in Rn here, call it omega. I think in general this lecture we'll call pieces of Rn omega and surfaces m. M stands for manifold. I guess in this class we usually use S. But anyway. One of our favorite tools from AP Calculus back in high school is integration by parts, right? And all integration by parts is the product rule in some sense. And one way that you can think about it is that when you write, so usually the way we write down integration by parts is something like this: integral of u dv equals, how does this go? uv minus integral of v du, I guess you could say. This notation always kind of bugs me because it's hiding like all kinds of technicalities and like how the heck do you actually evaluate these things. But that aside, if you look at our expression for integration by parts, hopefully this is something familiar by the way. What are we doing? Well, we started out with the derivative in front of v and no derivative in front of u, and then we swapped the two. Yeah. By the way, usually, what if you make this into a definite integral, right? Then this uv term here is evaluated at the endpoints, which is important, right? Because the endpoints are nothing more than the boundary of this little piece here. So if you go into higher dimensions than 1, right? This is the AP Calculus version of this, and now we go to the Math 52 version of integration by parts, right? Then basically the same thing happens. In particular, if we write down the integral over our domain omega of f times the Laplacian of g, remember the Laplacian is a second derivative operator, right? In fact, the Laplacian is just given, right? In fact, we should put it on the board. The Laplacian is, this is not very good mark. Laplacian is just the sum minus the sum of d squared dxi squared in when you're in Rn from I equals 1 to n. Yeah. So all we can do is basically apply this rule dimension by dimension, and what's going to come out is that you get, well, you get these boundary terms, right? That's that UV object that we had before, right? And now you're going to have this minus sign. And now what have we done? Well, this notation hides things a little bit. But basically, we've popped off one derivative from our Laplacian, remember Laplacian's second derivative, and we stuck it onto f instead of g. Right? And so you guys can kind of unravel this formula at home using these expressions here. And hopefully what comes out is true. Well, yeah, this is also Stokes' theorem. That's the better way to write it down, but it doesn't really matter. Well, I don't actually think it doesn't. Anyway, yeah. So hopefully we all believe this expression, whether or not we call it Stokes' theorem or integration by parts or what have you, it doesn't really matter. Yeah? Cool. So I just gave you an integral relationship involving Laplacian and the gradient operator, right? But our whole goal today was to write down an operator that is just a derivative, has nothing to do with integrals, right? So somehow we need to bridge this gap, and this is going to be where our tricks from weak PDE and some fancier levels of math are going to come into play. But they're actually not too complicated, at least if we're willing to ignore all the difficult convergence questions and so on, which of course I am. So anyway, let's say that I have a function on my surface, right? So hopefully we're all comfortable with this notation now, right? We're going to have an f that takes in points on M and returns real numbers. Yeah. One thing that we can do is write down this thing that we can call the L2 dual of my function, right? So if we start out with function f, then I can generate an operator called L sub f, right? Today we're going to use cursive L. And what this thing is going to do is it's going to take objects in L2 of M and return real numbers. How many of us know what L2 of M is, by the way? This is fun slang shit right now. Yeah, so that's let's clear. So let's keep our Laplacian there. Yeah, so hopefully, of course all I'm going to do is unravel one level of notation, but really going down far enough to define like what an integral is and so on. Yeah, so L2 of M is going to be basically the square integral functions on M. Yeah. So this is the set of f from M to real numbers such that the integral on M of f squared is less than infinity. Right? Some number that I can write down. Yeah, that's what L2 is. Cool. So L sub f takes functions as input. Right? This is different math. F takes points as input. L sub f takes functions of input as input and gives you back real numbers. And what is L sub f going to do? It's going to take f multiplied by g, right? G is going to be the function that you take as input. And it's going to integrate this product over the surface M. So everybody hopefully understands this direction of this arrow, right? If you hand me a function, I can hand you back this operator that now takes a second function and integrates against it. Yeah? This is going to be our cute trick for stepping around some of our derivative tricks. So, yes?
Is it clear that this is finite? I mean,
I'm sorry?
Why is it a number? Why can't it be infinite?
I'm sorry, what?
Why is the integral finite?
Why is this integral finite?
Yeah.
Yeah, Cauchy-Schwarz. Right? This is the inner product of f and g, right? In this L2 space, right? So that's less than or equal to the norm of f times the norm of g and L2. Right? So let's just prove this. Yeah. So one thing we can do is write down an inner product operator. Of course, all of this there's sort of a level of sort of rigorousness that's being left out. But that aside, the intuition is that you can write down we can write down the inner product of two functions and say that's like that. Yeah. And by the Cauchy-Schwarz inequality, the same one we have for vectors. Right? This thing looks like the inner product. Yeah. We can say that the absolute value of f inner product g is less than or equal to norm of f norm of g. Yeah. So where this norm operator squared is nothing more than the inner product of f itself. But we already said that all the functions we care about are square integral. Yeah?
So f is square.
I'm sorry?
So f is in L2.
Oh, sorry, I guess I didn't write it down here. In fact, that is an excellent question, and that is what is g? We're going to call g a test function. This is the thing we integrate against. And in particular, we're not even going to just say that g is L2. We'll say, sure, it's infinitely differentiable. Yeah, that's it. Or I meant to put c infinity in n instead of L infinity. I apologize. And that when you restrict to the boundary, it gives 0. Basically, you can think of this class of test functions as the class of functions that you sort of care about your Laplacian acting the right way on. And in fact, we can think a little better than that, right? Because oftentimes the story in analysis is that maybe we really care about L2, but I've written down functions in C infinity. No. But you can think of lots of functions, lots of square integrable functions as the limit of lots of differentiable things. So for example, maybe I give you this sort of top hat looking object, right? You can think of him as the limit of a bunch of sort of smooth things that become more and more square. By getting into what type of convergence and so on is that the scope for today. Yeah? So we now have this complete object, right? We take a function in L2, we take a class of test functions here, and we can generate this operator that integrates against them. Yeah? Cool. So one question that can be in the back of our minds is that have we lost any information by doing this, right? I told you how to generate L sub f from f, but one question is, can you generate f from L sub f? And the answer is yes, sort of. And one way to think about that is that remember this operator here. You get to play this game, right? Where I hand L sub f function and it gives me the integral of f against that function. But I can't actually observe values of f itself. Right? But one thing I can do would be, for example, to take little sequences of bars that get skinnier and skinnier and skinnier. Right? And this sort of localizes the behavior of f, and in that way we can recover, and again, this is a very intuitive argument that requires lots of analysis to get exactly right. But sort of intuitively, you can recover more or less the structure of f using this process. Yeah? Okay. So what have we done so far? We've taken a function and we've defined what it means to dualize that function in this L2 space of inner products. Yeah? Now, why do you think we did this? Well, remember our integration by parts formula that we had before, right? So I told you guys that discretizing a first order gradient is not so difficult. Discretizing the divergence is a little bit trickier. So we're going to avoid the issue altogether by only working in these dual spaces. Right? In particular, let's say that I want to take the gradient of some function f. Let's assume f is infinitely differentiable now. Well, let's say that I now take that Laplacian and I generate this linear operator L out of that, and I apply to a function g. I know there's a lot of words, but hopefully they kind of parse. Well, when we unravel our definition, that's nothing more than the integral of g against the Laplacian of f. Yeah. But remember, our integration by parts / Stokes formula / whatever tells us that we can take one of the derivatives off from f and stick it on a g, right? And now, of course, the question you should ask is what happened to the boundary terms? But I told you, I only care about functions g that are 0 on the boundary of my surface anyway. So they vanish. Yeah? Well, so what did I just do? I gave us this sort of backdoor way to evaluate at least something related to the Laplacian function without ever actually writing down the Laplacian of the function. Right? And this is what we're going to use in this sort of finite elements approach to derive a nice discrete Laplacian operator in a very clean way. Cool? So this is an example of this Galerkin approach to partial differential equations. Basically what you do is you have this multiple choice game where you need to decide what functions you care about, namely like whose Laplacian do you need to be able to take. And you need to decide on your set of test functions, right? In our case, we've decided that we care about differentiable functions that are 0 on the boundary of the surface. right? This is sort of one way to implement boundary conditions for your operator, by the way. Right? And then once you have all of these, you can take your favorite differential equation or operator and move it into this weak space. Right? We call this weak because it's just integrated against stuff. And that's going to be our way to implement this differential equation. So let's see this in practice. Yeah? Yeah.
I understand it's really gross.
There are a couple of things, right? So, I mean, that's an excellent question, right? Like, why are we being lazy? Why don't we just work it out? Yeah. So, first of all, the expression that I wrote down for the Laplacian there, at least, was in terms of these local coordinates, right? It had this matrix Gij, which is moving back and forth between parameterization and surface space and so on, right? And all of these little localized derivatives don't really exist on a triangle mesh, right? So while we're basically a theme that we're going to see this week and next week is that one way to think about a triangle on a triangle mesh is as sort of this integrated piece of the surface, right? That is that your triangle mesh really, right, if you have some straight line little piece of your surface, it might be an approximation of some God knows what wiggly object, right? But we can't see it. All we can do is make observations on the vertices and somehow some average value along faces, you know? Well, if our expression for the Laplacian is in terms of these like very localized derivatives that you take limit as things go to zero, right? You're right, one option would be to just say, to use this divided differences approach and just subtract and hope that things converge. It turns out that that's very difficult to do here because that expression you saw, it's quite nonlinear, right? And has 1 over things, which tends to numerically be pretty good. Our trick for integrating against things is that when we integrate against objects enough times, we sort of mollify this in such a way that we're going to be able to understand the overall behavior of Laplacian on a facet of my mesh rather than just localized at one point. Cool? All right. Any other questions, by the way, before we dive into discretizing this? We're going to do it in a lot of detail. Okay. So, one final observation we should make is that our expression for this sort of weak Laplacian integrated operator here, right, L sub Laplacian f, only needs one derivative, right? So as long as we can take one derivative of f and g, namely their gradient, life is good, right? So we started out at C infinity, but really C1 is enough for us. No? And then what this suggests is that we actually have a pretty easy basis for function space on the surface, right? So we've already seen this diagram once a couple weeks ago in this class, and now it's going to come back to haunt us a little bit more. And so let's say that I want to represent a function on a surface. Remember, a function on a surface is nothing more than an object that takes every point on my surface and maps it to a number. Yeah? Well, obviously in computer science, we can't do that for every point on my surface because there's an infinite number of them. But we've already approximated our surface with a big triangle mesh, and one of the most reasonable approximations of a function on that surface would be one value per vertex. Yeah? Well, one thing we might think about is then what is the influence of that one value per vertex, right? How do I go from this inherently discrete object to something that really does look like a continuous function from point to point to point along this mesh? And the finite elements version of this says that really this number that I'm assigning to vertex I has some little area of influence, right, that we call a basis function. Right, so does anybody remember what this thing that has label vi is called? It's called a hat function. Right? Looks like a triangle. Basically what it's saying is that when I write down a function on a surface, it's going to be a linear combination of one value per vertex. That's what this I is here. And if I want to evaluate this function at like the middle of this triangle here, all I'm going to do is say, take the value at vertex I, and basically linearly interpolate it between that and the other two vertices, right? In fact, those of us that come from computer graphics are quite used to this calculation because it's precisely the same as this barycentric interpolation that you learn for shading. That's all it is. All we're doing is barycentric shading per triangle. But now, instead of thinking of these values at vertex I as like, I don't know, your favorite Phong inner product, instead now they're just going to be some function and we want to evaluate it everywhere. Yeah? Alright. So so we call this a piecewise linear interpolation of a function, by the way. Why is that? Well, let's say that you zoomed in on a single triangle, right? Our interpolation of f on that single triangle is just some linear affine looking object, yeah? And it's piecewise because as you go from triangle to triangle, you have these little facets. Cool, so this is going to be our idea of function space, right? And h sub I is going to be the ith hat function around vertex I. Cool. Alright. So now, let's go back to our expression for this, this integrated Laplacian and sort of figure out what that means for us in the end. So remember that we've decided we're going to represent functions for now, both f and g, as linear combinations of hats. Yeah? So these are piecewise linear objects. So what do you think happens when I take the gradient of these functions? What am I going to get? Oh, you guys aren't very brave. Come on, somebody. Alright. Well, what happens when I take the derivative of a linear function? You get a constant, yeah? Now, is this function going to be constant per vertex, per face, per edge? What is it constant on? Each face, yeah. So all it is going to assign a different gradient vector to each face of my mesh. Yeah? Cool. Alright, so what's the next step? Now we have two gradient vectors, grad g and grad f. I take the dot product. This is going to give me what kind of object? What was that?
Scalar.
Yeah, it's going to give me a scalar. And where's that scalar going to live? Is it going to be a combination of hat functions anymore? I saw a no and then back to the laptop. Is it, so what is it? Well, if these guys are constant vectors per phase, we take their dot product, this is going to be a constant number per phase. Yeah? Okay. So then what do we do? Well, now we have to integrate this thing over the surface, but integrating a constant over a triangle is a pretty easy thing to do, yeah? It's just that constant value times the area of the triangle. So we've taken this pretty complicated expression and actually made it into something pretty easy to compute. And let's unwrap it a little bit more and get an actual honest-to-goodness weak Laplacian operator. So never mind the fact that we're on a whole triangle mesh here. Let's say our triangle mesh is a triangle, and we want to figure out what our operator is doing there. Right? This is a predictable story from here. Right? All we're going to do is sum to get what we actually care about. Yeah? So remember that our hat function is this linearly interpolating object that is 1 at the vertex that the hat is centered on, and 0 at all of its neighbors. Yeah? So we'll call our hat function f for now. I guess I should call it h, but too bad. So, what do we know about our hat function? Well, I've never actually written the function down for you. You could, but we're actually going to kind of circumlocute. We're gonna be tricky and step around it a little bit, and write down some properties that we know are true. So first of all, the easiest one, right? Our function is a function along the surface, right? So if we take our gradient, we know that the gradient has got to be tangent to the surface, right? Because the function doesn't even exist really when you leave the triangle. So grad f dot normal is 0. Cool. All right. Now, how did I get these other two relationships here? No, this is a linear object as you move up and down the triangle face. And in particular, one nice property about linear functions, at least geometrically, is that then if I take a straight line and restrict my function to that straight line, it's still linear, right? So all this is saying is if I take the derivative of f in the v1 to v3 direction, or I guess, v1 to v3 to v1 direction here, right? And subtraction goes this way. What do I get? Well, it's pretty easy. I just subtract these two values, right? Because divided differences works exactly on linear functions. Cool? So all this is saying is that on this edge and this edge, I know the derivative of f. It's pretty easy to write down. Right? And I get it by taking the gradient and taking the dot product of that with the direction that I'm taking the derivative. Cool? Now, there's a cute trick that we can do here, which is that we notice that both this term and this term involve v1. Yeah? And when we subtract them, the v1 goes away, and the 1 on the right hand goes away. And what did I get in the end? I got grad f dot this vector, v2 to v3, equals 0. Yeah? So what does this tell us about the direction of grad f? Well, we know that grad f dot n is equal to 0. We know that grad f dot this vector is equal to 0. So it's got to be perpendicular and point, just perpendicular to the bottom edge of the triangle. This is great. We just took a vector problem, made it into a scalar problem. There's only one direction to care about.
Is the choice of the edge arbitrary then?
This is just some triangle with vertices v1, v2, and v3. I haven't told you anything about where it's. Yeah. Cool. So to make life easier, I rotate my triangle by about 30 degrees. And now that direction is up. So, what do we know? Well, remember we had this expression from before, right? The grad f dot the difference is equal to 1. So now let's unravel that expression a little bit. Right? So remember the dot product is nothing more than length 1 times length 2 times cosine of theta. Yeah, hopefully this formula that we're pretty good at by now. So in this case you get length of grad f, and then remember this is v1 minus v3. Yeah, so this edge here, so you get an L3 term here. And then cosine of theta, you be a little bit careful about what your angle is here. Right? But if we take this gradient and move them over to the vertex on the right, yeah. And then what is the angle? It's from this edge to your gradient here. Maybe I should draw this instead of waving my arm around. My posture. Sorry. So here's my triangle. Right here. So I can translate grad f anywhere I want. So let's put them on the right vertex. Right? And we have that. This has length L3. That's the 3 downstairs. This angle is theta. Right? These two things make 90 degrees, so this is, I over 2 minus theta. Yeah? So now we get this L3 times the length of this vector times cosine of that angle. Yeah? Thankfully, we have a pretty good expression for cosine of pi over 2 minus something, which is sine. And this implicitly, now we just divide by the L3 and by the sine here, gives us an expression for the norm of grad. Right? And what is it? Well, it's 1 over L3 times the sine of this angle down here. Yeah? But that's nothing more than the height of my triangle, or 1 over it. By the way, this calculation should look somewhat familiar from when, about 2 weeks ago, we took the gradient of the area of the triangle mesh. This is more or less the same kind of trick. In fact, we'll see if that's not a mistake in a minute. So anyway, if we like very slick notation, one thing you can notice is that if you take E23 and just rotate it this way, so you keep his length there. Remember that area is nothing more than 1/2 base times height. Multiply by that by 2, and I get base times height. Now I'm going to cancel out the base by leaving the length of E23 there. I just rotate by 90 degrees. So this is the same expression, just a little bit, cuter. We like cute. And this is the gradient of a piecewise linear function on a triangle. Right? Not so hard. And we got there without actually ever writing down the function, by the way. Kind of slick. Remember that we've already played a game like this, right? We took the gradient of the area of a triangle mesh with respect to his vertex positions. And if you go back into your lecture notes, you'll notice that the gradient of the area, the expression that we got here, looks awfully familiar, right? It points in the same direction. It does not have the same length, but it's pretty easy to write down a relationship between these two things. For now, it's not too useful, but I think next week, actually, we'll think about these connections a little bit more deeply. Anyway, so remember, what did we actually need, right? So I just wrote down an expression for grad f, but we're not quite done, right? We need to do all of these inner products and areas and so on. And so we'd like to unravel this as much as we possibly can, and we're almost there. Yeah? So now, rather than thinking about a single triangle, let's think about hat functions around vertices, right? Well, all that hat function is the sum of a bunch of linear functions on all of his adjacent triangles. Yeah? So we're going to have to do sum a little bit carefully. So let's say that I wrote f and g in terms of, in terms of hat functions, and now I want to take their inner product of these gradients like this. Well, remember that we're eventually going to write f and g as the sum of a bunch of hats. So for now, let's think of f and g as a single hat function. Yeah? Now, for the most part, these inner products are going to be 0. Right? If f and g aren't at least adjacent, like here's one vertex and here's another, then their one ring on this triangle mesh just doesn't overlap, right? So you can take as many derivatives as you want, and nothing interesting is going to happen. Yeah? So that leaves us with sort of two cases. Yeah? So what are the two times that hat functions can overlap? Well, the first one is going to be when you have the same vertex. So here's some vertex. Yeah? Again with non-standard valence, because I can. And maybe I take the inner product of the hat function centered at this vertex with itself, right? And what's the only other time that the hat functions can even overlap? Well, I can take the inner product of the hat function centered at that vertex with the hat function centered at any of the neighboring vertices. And hopefully you guys agree with me that anywhere else the inner product is 0. So let's do these two cases. So first, let's say I give the same vertex twice, right? All this is going to be is the integral of the norm of the vector grad f, or grad hat, I guess, squared, right? Dot product of something itself is this norm squared. Well, remember that we already have all kinds of slick expressions for grad f, and in particular, we actually wrote down his norm. So integrating this over the triangle, like we already discussed, is nothing more than multiplying this constant value times the area. Yeah? And since, remember, that the norm of grad f is 1 over the height of the triangle, that was from a few slides ago. Well, so the norm squared is this height 1 over height squared. If we like, area is 1/2 base times height, so we substitute that here. And then if you go back to our lecture, and I probably should have copy and pasted that slide here, but such a slide. If you go back to the lecture on how we took the gradient of the area of a triangle mesh, we actually already did this calculation, right? That the ratio of the base to the height of a triangle can be written in terms of the cotangents of these two angles, alpha and beta. Yeah? And all it is just the average of the cotangents of these two guys. Right? So this is something we already proved. We can go back and double check that for lecture 8, I think. And yeah, so now we have an expression for basically the diagonal of the matrix we're going to write down. Now we have to do something slightly trickier, which is take the inner product of two adjacent vertices hat functions. Yeah? Notice that we're still on a single triangle, right? We've still got a sum around the vertex, but that's going to be the easy part. Yeah? So what do we have now? Well, let's say that I have f sub alpha and f sub beta. What does that mean? Well, f sub alpha is going to be the function that's 1 at the vertex with angle alpha and 0 with these two vertices. F sub beta is going to be 1 at the vertex with label beta and 0 at these two guys. Right? They're both linear. So what happens? Well, we know that the gradient of f sub alpha is perpendicular to this edge. We know the gradient of f sub beta is perpendicular to this edge. Right? That should be the picture that we have in our mind. So let's do our calculation here. Remember that we're going to integrate over the triangle, this inner product here. Notice that even though I've chosen two different sort of starting vertices, this is still the inner product of two constant functions on my triangle. So I still get the area of the triangle times this inner product. Notice I'm sort of abusing notation a little bit here, that this gradient you should think of as a function of the triangle and this is a constant, but that's sort of a pedantic point. Anyway, so let's go back and explore what all of this means. So remember that one way to write down this gradient is edge rotated 90 degrees divided by the area, right? 2 times the area, I guess. So 2 times 2 is 4. And we already had one area factor here, so the area squared, we just get A. Yeah. And again, we just get inner product of these two rotated edges, right? Well, if you go back and convince yourself, so again, what is our favorite expression for inner product? Well, it's just length 1 times length 2 times cosine. right? And in fact, since we have this 90-degree rotation here, we can double check that you get a minus sign that comes out of that. You see, I think I shut that. I'll keep this small back here. It's the best way to think about where that minus sign is. Oh, yes, okay, sorry. So let's draw a picture actually. Okay. So E31 is this one, right? Here's my triangle. Then we're doing. So we'll do. Okay. Counterclockwise? Yes. Okay, we're good. So here's our triangle, and we want the inner product of these two vectors. And we'll call this angle theta. Right? The inner product of two things rotated 90 degrees, the same thing as the inner product of those two things not rotated 90 degrees. Right? And if you look at it, basically the two vectors you're inner producting are this one and this one. Right? So one thing I could do would be to take this guy and flip his sign like that, and now it's L1, L2 cosine of theta, right? And the minus sign comes in because really his orientation is like this one. Okay, that's a good play. So anyway, this is our expression here, and now we can do our same substitutions that we've had from that old lecture, and what eventually comes out is minus 1/2 times cotangent of the angle between those two guys. Kind of an interesting expression, right? We started out with the basis function with these two angles, and what comes out is the cotangent of the third one. Okay, so hopefully I haven't lost everybody. I know there's a lot of calculations, but this is a humongously important matrix, so it's worth making sure we know where it comes from. Yeah?
So, was there an assumption at some point that edge 2, 3 is at the bottom of the half?
By construction, right? So what we did is we just said, okay, for some arbitrary triangle, we're just going to number the three vertices and call edge 2, 3 or 1 at the bottom.
Sorry, I missed that.
No, yeah, no problem. All right, so now we know how to inner product functions on a single triangle, and all we have to do is sum around a vertex, and we're good to go. Yeah? So remember we had two cases, right? Either we take the inner product of a hat function with itself, or we take the inner product of the hat function of the neighboring hat functions. Yep. So what happens in these two cases? Well, the inner product of hat function and yourself, remember that what ends up happening is you get the cotangent of these two angles here, right? The average of those two. So when you take the inner product of the whole hat function, all you do is sum around this vertex, all those cotangents. Yeah? Here we are. And what happens if we have two vertices P and Q? Well, remember that our expression in that case, the inner product involved the third angle that didn't touch either of those two vertices. Right? And basically, the piecewise linear half function at P touches both this triangle and this triangle, so we just sum these two inner products. Cool. So now we can write down the inner product between any pair of half functions. Remember our rule, if you get the same half function twice, you use this guy. If you get two adjacent half functions, you use this guy, and otherwise it's 0. Right? If you recall, these weights that I just wrote down are precisely the same weights that we wrote down when we took the gradient of the area of a surface, and that's not a mistake. In fact, Laplacian and surface area are quite closely related, and that's something we'll hit in the TP. Okay. So in particular, I can take all of these interior angles, and I can construct a matrix Lij. This is called the cotangent Laplacian, and if there's like one phrase that can stick in your brain at the end of this course, at least from my perspective, it's probably this one. That one, I guess, cotangent Laplacian. Remember the expression, you get extra credit. And basically, the cotangent Laplacian is exactly what we just spent the last half an hour constructing. Right? And it's this thing that gives you a relationship between adjacent vertices, like these guys, or the same vertex, and 0 otherwise. And it involves, and this perspective on the cotangent Laplacian is that that it gives you the Laplacian of a first-order finite element system. Notice that I also could have defined this 2 weeks ago, right? When we talked about curvature and we took gradient of surface area and got these same weights out, I can see the cotangent Laplacian is the matrix that when you apply it to vertex positions, you get gradient of area. That's exactly the same matrix. And next week, we're going to see it in terms of discrete exterior calculus, which is a fun tool and a mouthful to say. So now, finally, we can start to do interesting things with this object. And let's think about a few. So probably the easiest model equation that we can think about solving is the Poisson equation. How many of us have seen the Poisson equation in some context? Interesting. I think it's at a hand speech these questions. So the Poisson equation says I want to find a function f. F is our unknown, such that when you take his Laplacian, you get a second function g. Right? So down here we have two solutions to the Poisson equation, where what these people have done is their boundary conditions are that the equation, the function f has to be 0 on the boundary of the butterfly and the ear, I guess. And for g, they have chosen the function that is just constantly equal to 1. Right? So what does that mean? Well, remember that the Laplacian is a sort of measure of how concave your function is. Right, so saying you want your function to sort of look like a nice umbrella. So if you set g equal to 1, then you're saying you want this function to just kind of point down like that as much as you can everywhere. Right? So when they fill in values, right, it's got to be 0 on the boundary, and then it has this nice sort of arc upward in the interior. Right? So our goal is you give me g, I give you f. And we're going to use our Laplacian to do that. So remember that we now have to translate everything, right? This is called a strong equation, right? This is in terms of the derivatives of f. But now we have to put everything in this weak formulation that we've written down, which is in terms of these integrated quantities. Yeah? Well, remember that our equation, again, which is Laplace of f equals g, right? The only thing we might do is say that a function f is a weak solution of the Poisson equation if I take any test function phi, right, and I just multiply it on both sides of the Poisson equation, integrate, and get an equal sign all the time. This makes sense? This is a definition of a type of solution to this PDE. Right? And again, it involves this sort of funny game where we don't actually observe function values, we observe integrals against function values. Okay? But in some sense, if you like the backward argument, all we do is multiply the Poisson equation on both sides by phi and integrate. Yeah? So certainly the Poisson equation is true, then this is true. And now we're gonna work in the backward direction. So remember that our game, right, if we use this Galerkin method, is that we have to write down a set of test functions, a function space, and then sort of chase out what all of our coefficient means. So in this case, we're going to worry only about hat functions for both tests and for our function space. What does this mean? Well, the definition of a weak solution of the Poisson equation then is this boxed guy upstairs, right? That for all hat functions h sub I, the integral of h sub I against Laplace f is equal to the integral of h sub I g. Yeah. Again, all I've done is taken Laplace f equals g, multiplied it by the functions that I care about and integrated. Is that it's got to hold true for all the functions I care about. Notice this is a bit of a lie because I put the Laplacian here, but remember that we only have one derivative when we talk about Poisson's linear hat functions. So really, we've got to use our favorite expression downstairs. Cool? So anyway, let's expand the left-hand side like we usually want to do. Right? So this is the integral h, which this is sort of a definition, and so in the way we construct here, right? The integral of Laplace f against this hat function. And well, remember that f is also going to be a linear combination of these hats, so I go ahead and substitute that here. Right? So now we have one value per vertex times each hat function, and all you do is move this sum to the outside. Right? And then what do I get? Well, I get this value per vertex, a sub j. Right? And then in the inside, we get the inner product between the gradient of one hat and the gradient of another hat. Okay? This sum. But luckily for us, we already wrote down exactly that matrix of inner products. Right? And that's this cotangent Laplacian f. right? So in other words, if I wrote A as a vector of values, right? So A sub j is the jth value of A. And then this is just matrix vector multiplication, right? So pretty easy to compute. So what are we going to do with it? This expression is more complicated than it looks. In fact, actually, I already told you what it is. So if you ignore the left-hand side, basically all I'm saying here is now let's take remember grad f, and we're going to integrate it against each one of our hat functions, h1, h2, h3, h4, h5, and so on. Yeah, we're going to stack all of those integrals. Right, each one is just some scalar number. We're going to stack them all on one long vector. Well, we just told you in the last slide that that's nothing more than this sum here, right, against this matrix L, and that's just matrix vector graph. Right? So if I want to get the integral of this hat function, this combination of hat functions written down in the spaces, against each, the integral of the Laplacian of that against each of the hat functions again, does this make sense? Then all I have to do is compute a matrix vector problem. Pretty easy. But we have a problem. Remember that our Poisson equation, yeah? It's not just the left-hand side of this. You got to have a right-hand side too. And we haven't decided how we can deal with that yet. So remember, in weak PDE land here, we're going to keep integrating things against test functions, right? So our left-hand side we now know how to deal with, right? It's just Laplacian times that vector coefficients. But what about the right-hand side? Well, we need the integral of whatever our function is against the hat function h sub I. This isn't a calculation we've done yet, and in fact we're in a little bit of trouble, right? Because what happens if I take one piecewise linear function, right? This is sort of a 2D hat here, and I multiply it by another piecewise linear function. What's the product of two linear things? It's not linear anymore, it's quadratic, right? In fact, you get this sort of funky looking pointy object here, right? This sort of breaks our intuition a little bit for how this finite elements thing should behave, right? That we kind of hope that we're always staying in this nice linear space, but such as life, that just doesn't happen. So we have to come up with a way to deal with this problem. And there are a lot of ways out. The first one is, well, we can still just do this integral. It's not such a hard integral. And this is called the consistent approach to finite elements. Or we can make a couple more approximations. Or we can redefine what we think of for this function g. Today we're going to talk about the first two options here. Alright. So just like we wrote down our cotangent Laplacian matrix as Lij, remember it's just this matrix of all of these different inner products. We can do the same thing here to make what we usually call a mass matrix or an area weights matrix. We'll call it Aij. And all he is the matrix of inner products of the hat functions themselves. Right? So no longer do we have any sort of gradient in here. So let's step back and think about what this matrix is telling us about life. So the diagonal elements of this are just h sub I squared integrated over the surface. So you think of that as the norm of that hat. Okay? And the off-diagonal ones are the overlap. So what can I tell you about? So what can you tell me about vertices that are not adjacent on the mesh? So let's say vertex I and vertex j are on like the opposite sides of my mesh. What's going to be the value of Aij? No. 0. Thank you. Yeah, so this is still a very sparse looking object. By the way, on your homework, I'm going to have you construct all of these things to make sure that you 100% understand all this stuff. And if you do not store your matrices as sparse matrices in MATLAB, we're going to make sure you get 0 credit. Like literally 0. I want no credit if your matrices aren't sparse. Cool? Cool. Alright. It's like one line in MATLAB, but otherwise your computer's going to explode. In fact, I'd be very impressed with your laptops if it manages to do this in a non-sparse way. But just so you know. So one thing I could do, and we're not going to do the integral here because it's like a little bit, it's not hairy, but it's kind of annoying, is actually just write down all these inner products, right? Now we have to integrate quadratic things instead of linear. And in the end, you get this kind of nice expression, which is that when I and j are the same vertex, you get the area of the triangle over 6. When I and j are different vertices, you get the area of the triangle over 12. And that is our consistent mass matrix. right? So this is, and by the way, in your homework, this is what I'm going to ask you guys to implement. In practice, we don't use it a whole lot. We'll explain why in a moment. But yeah, so if you want to solve a completely consistent, weak-looking, finite elements version of Laplacian or the Poisson equation, right, then your right-hand side is just going to involve this area matrix here, which is very easy to construct, and then life is good. Of course, remember this, again, is for a triangle, so we have to continue playing the same game we've already played a number of times. It's somewhere on the one ring. And thankfully, it's very predictable what's going to happen, right? So if the integral, if the inner product of a vertex in itself is the area of a single triangle over 6, then the inner product of a hat around a vertex in itself is just the area of the one ring divided by 6, and so on for the adjacent vertex case. Yeah? So what is this matrix doing? Right? So why did we get 1, 6 and 1, 12? Well, for one thing, we notice 6 and 12 both have one common factor that seems to be important on triangle meshes, namely 3. Yeah? So what is this matrix doing? Well, it's taking the area of this triangle and sort of partitioning it among the 3 vertices in different ways. Right? In fact, one way to think about these 6s and 12s is that you have 1, 2, 3, 4, 5, 6, right? You can count all the different ways that you can take 2 vertices and combine them, right? This is, or rather 3 vertices and combine them. It's not 3 choose 2, it's 3 permutation 2. And so all it's doing is taking the area of the triangle and partitioning among all of his neighbors, right? Now, unfortunately, so if, in particular, if you go and you look at this mass matrix, you can check this at home, or do it in your head right now. First of all, the rows of this matrix sum to the one ring area around a vertex divided by 3. Yeah. This matrix certainly only involves a vertex and its neighbors. And you leave it as partitioning surface area. Now, why do statements 1 and 3 kind of make sense here together? Like, where did that 1/3 factor come from? Well, how many different vertices does a single triangle touch? It touches 3, right? So if you're going to have the area of a one ring, yeah, so here's vertex, right? We're going to worry about the area of this entire object, right? Then we're actually going to sort of triple count this area, right? Because his one ring overlaps with his one ring by these 2 triangles, right? So this 1/3 factor is that the area goes to each of the 3 vertices. But in general, all this thing is just this guy that's partitioning the area of your surface in a particular way. And we can use it for a sorted object. So let's say that I want to take a function f and integrate it on the surface. And f is written in this hat function basis. Right? Well, f is nothing more than f times 1, last I checked. Yeah? And one way to get the constant function 1 on the surface is to just, oh, sorry, I skipped a step. Actually, so we can write a f as this combination of hat functions, a sub j, h sub j, yeah? And then you can write 1 as a combination of hat functions as well, right? All 1 is the sum of hat functions all with the same coefficient 1 next to them, right? Then we're going to apply, remember we seem to have like 3 tricks in this class, right? Substitute your favorite hat functions and then pull the sum out of the integral, and we're going to do it again. We're going to take the sum over j and the sum over I and move them to the outside. Right, so what's going to happen in the interior is you get integral of h sub I times h sub j over m, which is nothing more than this matrix A that we already defined. Right, so in other words, this matrix A can be used to do calculations like integrating functions over the surface and so on. Right? What is the surface area of the surface in terms of A, by the way? What's one way to recover surface area as an integral? You integrate 1, right? So in other words, you would get 1 transpose times A times 1 again, right? And by the way, if you think about it, that expression is nothing more than the sum of all of the elements in A. So that's a very slick way to show that this thing is partitioning the area of your surface. Yeah. So in many ways, really, what all this matrix is doing is just telling us how function values at vertices interact with their neighboring triangles when we think about these integrated schemes. But it's kind of annoying to deal with this matrix A. In particular, remember our Poisson equation here. Or what happened to the Poisson equation when we discretized it is it turned into a slightly different matrix equation, right? You got that the cotangent Laplacian times your vector of hat function coefficients is equal to the area matrix times this vector, times the vector of coefficients for your right hand side. Yeah? So now, every time we deal with matrices, we got to deal with two matrices, and that's not so great. And in fact, every time we want to deal with L, it would be nice to not have to invert L and A, or have to constantly multiply by all these different things and so on. And so one thing we could do is try to approximate this matrix A with a diagonal matrix, right? Keeping in mind that basically all A is doing is integrating functions on the surface. So this approximation is a very well-studied object in finite elements. It is called the lumped mass matrix. And we've actually already thought about it a little bit in this class. So one alternative view for how you might integrate a function on a surface, remember, is to associate this dual cell with each vertex, which is sort of the area associated with that vertex. Then an integral of your function is nothing more than the sum of vertex values times the areas of the dual cells. Right? We remember that? I think it's from week 5 or so. So it turns out that a good approximation of your matrix A is to take all of these little off-diagonal neighboring values and stick them all on the diagonal in such a way that we say that our new approximation A tilde of the mass matrix is going to be just a diagonal matrix with the cell of each vertex stuck along the diagonal, the area of that cell. Right? And there are lots of different justifications for this that vary from very, very high level, like what I'll probably use, to very careful convergence arguments that show that as you refine your mesh, you're going to get similar results regardless of which area matrix you use. From a practical standpoint, one way to think about it is that if we think of functions as not varying a whole lot from vertex to vertex to vertex, right? Then the value of some function f here and the value at just only one of its neighbors is going to be very small, right? So if I take these area weights and multiply it by this guy or this guy, it's not going to make much of a difference. So if I move it all to the diagonal, that doesn't affect my solve a whole lot. And in fact, this is actually one of many ways to get to a convergence argument for why this trick works, right? Because what happens as you refine your triangle mesh, right? These triangles get even smaller and smaller and smaller and smaller and smaller, right? But what does that mean about the function values at these vertices? Well, the vertices are getting closer to one another, right? And our favorite, localized properties become true, right? That if I have some function like this, right? And here's 2 points, and now I sample the function closer and closer and closer, right? These values get closer together. And so that's basically all this convergence argument is doing. So this leaves us with a choice to make, right? Which is, what is the area of cell I? And there are lots of different choices we can make here. Next week, we're going to actually explicitly lay out, I think, about 3 or 4. But for this week, at least, there's one simple solution, which is you say, well, for each triangle that's adjacent to a vertex, just take 1/3 of his area and stick it to each of the 3 vertices. And this actually is used in practice sometimes. And it's a perfectly reasonable scheme and perfectly convergent and so on. What this corresponds to is if you take your triangle and you find its barycenter. People in computer graphics are very familiar with this term, but basically all it means is if you think of these 3 points as vectors and you average them, that is the barycenter of my triangle. And I'm just going to partition my triangle through this barycenter point. And lucky for us, that gives us equal areas for these 3 pieces. Kind of a fun geometry exercise to do at home. Of course, if you take a look at the cell around a vertex that comes out when you do this, it's kind of funny shaped, right? Because none of these triangles talk to each other in any intelligent way. Right? So you can see in this case, for example, that your barycentric cell around this vertex is sort of, it's not even convex, which is somewhat suspicious. So for example, one option that we could have used that we didn't here would be that rather than using the barycenters, we construct the Voronoi cell of this vertex, right? That's the set of all points that are closest to this guy and any of his neighbors, and use the area of that. This is another option, but the Voronoi cell has other annoying properties, like it might leave the adjacent triangles. So anyway, there are lots of different engineering trade-offs that happen here, and you should proceed carefully. Or don't, and maybe, once again, since these are all approximations of one another, they'll come out to be very close. And it's only when your mesh contains very oddly shaped triangles that these cases start to matter. So, once again, our two ingredients for the day are this cotangent Laplacian matrix L, and this matrix of area weights A. And we have a decision to make for A, namely, are we going to lump the mass or just do this in a consistent way? The cotangent Laplacian L was gotten by a very simple sort of piecewise linear nice construction. Right? And together, these are going to enable us to solve all kinds of fun equations, some of which we've seen and we'll see in lecture, and some you'll see on your homework. For example, remember that we set out to solve the Poisson equation, but I never actually showed you what it looks like, right? Our construction was a little bit hairy because I went all the way through all the detail of this, but in the end, all we have to do is solve a pretty simple matrix equation, right? L times the coefficients of F is equal to A times coefficients of G, right? In MATLAB, once you've implemented your cotangent and area weights, right, some of the Poisson equation is a one-liner. In fact, it's one character, right? Because MATLAB has that handy backslash operator that solves linear systems, right? So let's say that I took Homer Simpson, and for some reason I decided that my function g should be 0 on his bottom half and 1 on his upper half. Turns out actually this function g doesn't quite work because the Laplacian has a null space, right? Namely, if I have a constant function on my surface, like 7 everywhere on the whole surface, right? The Laplacian of that function is 0, which means that this matrix is not invertible. But it's invertible for any function that integrates to 0. So actually what I do is basically plus 1/2 and minus 1/2, assuming that his area is 1. And in the end, I solve the Poisson equation, which you guys should check at home, right? And once you complete your homework, you'll have a cotangent Laplacian. You can play all these games, right? I do backslash, and out comes Homer with a nice, smooth thing that comes out. And by the way, something that I didn't talk about today that's kind of nice is that second derivative looking operators like the Laplacian correspond to positive definite matrices in numerical land. And PDE, this provides something called elliptic regularity, meaning that even though this function that I have on the left-hand side is discontinuous, right, 0 to 1, the thing that comes out of solving equations like Poisson is guaranteed to be smooth, right? And you can convince yourself that this is sort of a reasonable-looking version of what the solution of Poisson should be, right? It's some transition like this, because this is giving me second derivative values. Cool. This is by no means the only thing we can do with this operator. You guys will do a couple more on your homework. Like we discussed before, right, we can try and find vibration modes of the surface. So if I take Homer and I took him out of play and I hit him with a hammer and I observe where his surface is vibrating up and down, these correspond to eigenfunctions of this Laplacian operator. And indeed, finding these nodal sets and these frequencies and all of this additional information is as simple as just an eigenvector calculation on this cotangent matrix that we've written down. And it has this very nice geometric structure, right? So you can see this low frequency second eigenfunction. By the way, just like we just discussed, what is the smallest eigenvalue of my matrix? Somebody? Yes, it's not an appropriate answer. But what is the smallest eigenvalue of this matrix? The Laplacian. It's 0, right? Because constant functions are in the kernel. Yeah? But anyway, so ignoring the 0 constant function, eigenfunction can get all these other nice vibration modes. In fact, you can go very high with this if you want, right? So here's the 25th, 50th, and 100th Laplacian eigenvectors for Homer here. And these are all very easy to compute. So we can take these pretty complicated geometric problems and actually solve them using just a couple lines in MATLAB once we've constructed the tools we need. Another thing we can do, remember that heat equation has this very nice diffusive property to it. And a very classic application of this sort of Laplacian structure is to smoothing out surfaces. So in your homework, you're going to implement a method called implicit fairing, which basically solves the heat equation on the vertex positions themselves to smooth out a piece of geometry. And once you have your cotangent Laplacian, it's going to be a one-liner to implement. Kind of nice, right? There seem to be relatively few SIGGRAPH papers we can write these days that are one-line MATLAB code. So you'll take Homer and you'll make it into weird smooth that Homer. But as the figures in the paper suggest, the real applications for this sort of technique involve taking noisy scans of 3D shapes and making them nice smooth scans of 3D shapes. So anyway, today we've gone in excruciating detail through the derivation of this cotangent Laplacian operator, which is going to be hugely important for basically the remainder of this course almost. This is going to keep popping up in different places, right? We accidentally saw it a few weeks ago when we took gradient of area. We see it today when we talk about finite elements. Next week, we're going to talk about D's and stars and our favorite operators in the exterior calculus. And when we implement those, we're once again going to see that even though we've now approached calculus on the surface in a very different way, the operator that's secretly, this matrix we're computing, is secretly just a cotangent Laplacian once again. Right? So this operator just keeps reappearing in discrete differential geometry. And it can be used for all kinds of interesting calculations. So you'll do a few on your homework, and we'll see a couple more in the coming weeks. And I guess we'll stop there for today.